Hello and welcome back to our series in statistics. We're coming to you from the Arts Center, and today's topic is the Central Limit Theorem. Revisit. This is presentation 7.2, and we're going to illustrate the Central Limit Theorem by way of this example here. We have a random variable x denoting a population of stats 251 marks. They're normally distributed, with mean is 70, standard deviation 10, and within one standard deviation, or plus or minus 10 units of 70, 2/3 or 68% of the time, the x values will fall. That is between 60 and 80. Now we're going to look at sampling distribution based on sample size n equal 25. We've taken some examples here. If you take a sample of n equal 25, the sample mean should cluster somewhere around the middle here. We're trying to depict that on the screen here. And we're going to draw the sampling distribution here. Is much tighter. The x bars will cluster very tightly compared to the x values above. The mean will be around 70, and standard deviation in the x bars will be around sigma square root of n, or 2.0. So 68% of the time the x bars will fall between 68 and 72. And as the sample size increases, these estimates become more and more exact. Now we're going to illustrate this theorem with this Excel output. We have here 100 samples, each of size up to 1,000, and we're going to take the first 9 of these numbers, the first mean of this first 9 numbers, and we've depicted them down here. So we're looking at samples of size 9, and you can see here these sample means will indeed cluster around the population mean 70. And you can see somewhere as low as 59. And we're suggesting that these sample means will cluster around 70. See them coming on the screen here. And the average, or the mean of these sample means, we find the average or mean of these 70.10 compared to the theoretical value 70. The standard deviation in these means is 4.04 compared to the theoretical 3.33. And this gives rise to this symmetric region above the mean within which 95% of the sample means will fall. And we're just comparing the sample values with the theoretical values. 19 out of 20 of these sample means should fall in this interval, 63.47 to 76.53. And we're going to repeat that for n equal 25. You see them coming on the screen here now. Note the variability here is less than previously, sample size 9. The sample means will cluster around 70 again. The mean of the sample means here, these things in the yellow, 70.12 compared with 70. And the standard deviation will be 2.0 theoretically, and we find the standard deviation in these 100 sample means 2.08. And we're just comparing the sample with theoretical values. And this means, of course, that 95% of the time the x bar will fall between 66.08 and 73.92. Now we're going to look at sample size 100. Same as before, or sample size 100. Sample means will cluster around 70. Standard deviation will be around sigma square root of n, or 1. Now these are the theoretical values over here on the right, and these are your experimental values if you wish. And note how close they are, very close indeed. And looking up here, 95% symmetric region about the mean 70, within which 19 out of 20 of the sample means will fall. And that's contained here in this upcoming result. Now looking at the box plots for these sample sizes, we have here the data from the previous Excel output, and we have the box plot for the population, and the population will be roughly normal. But when we go to sample size 9, the sampling distribution becomes much tighter. N equal 25 tighter again, n equal 100 tighter again, and for n equal to 1,000 is so tight, in fact, that the distribution is essentially much like a spike. And now you can see the results coming on the screen here. We're going to apply this. If we're looking at a large population of workers at a construction site, we want to find an estimate of the blood pressure, systolic blood pressure, all we know, or given here in this illustration, is the standard deviation is 13.6 millimeters of mercury. And we're saying that the distribution of sample means will be roughly normal, and the mean will be unknown in this case, but sigma sub x bar will be sigma over square root of n, and we're saying we know what sigma is given in the problem. So we're simply taking these sample n values, putting them in here, and we find that this 60% symmetric region about the mean, which we don't know, is 3.4. For n equal 25, that reduces to 2.72. For n equal 64, 1.70. And for n equal to 100, 1.36. Now understand that that is the plus or minus error term here about the population mean. Now it turns out that if we specify a standard error of 1.2, we simply substitute it in here and simply solve for n. You can see we're cross multiply, squaring, and you can compute this on your own. So the conclusion is, to be as accurate as possible in finding an estimate of a population parameter, we should shove up the sample size as large as possible. And that concludes presentation 7.2. We ask you to review once again, take notes as required, and proceed to 7.3.